If you've been following the AI space, you know the real action isn't just in the big foundation models anymore. It's in agentic AI. These complex systems that are built on top of those models, the ones that can plan, reason, and actually use tools to get things done.
Exactly. And when you're building those systems, the biggest challenge isn't just more power, it's adaptation. I mean, how does the agent learn? How does it get better from its own mistakes? The whole field just exploded so fast, and we really needed some structure, which is why this paper we're looking at today is, I think, so important.
So what's the goal here for you, the listener?
Our mission is to basically unpack the framework from this paper. It unifies all this chaotic research into something systematic. It gives you a roadmap for, understanding and building these cutting-edge systems.
Okay, let's get into it then. The research divides the whole design space into two fundamental pillars. You have agent adaptations on one side and tool adaptations on the other. That alone really helps clarify things.
It really does. So let's start with the agent. That's where the intelligence is supposed to be, right? The paper categorizes how the agent learns based on the signal that is fully camera. Well, that triggers the change.
And there are two main forms of that signal.
The first one is tool execution signaled adaptation. Think of this as really fast, low-level feedback. A tool returns an error code, or maybe the environment says, yep, that worked. It's immediate.
And the second one?
That's agent output signaled adaptation. This is much broader, higher-level feedback. This is a person rating the final output as, poor quality or something like that.
Okay, so I can see the trade-off right away. Tool execution gives you that speed, that low latency, but the feedback is really narrow. It's just a yes or a no, basically.
The 0 or 1, yeah.
But the agent output signal sounds much richer, much more precise, but also way more expensive to get. Is that the idea?
That's the core distinction, absolutely. It's latency versus semantic depth. If you need your agent to tune itself continuously, in little steps, you lean on that tool signal. But if you need a total rethink of its strategy based on the final outcome, you need that expensive high-level feedback.
Right. Okay, so now let's flip it. This is where it gets really structured, I think. Looking at how the tools themselves get adapted. The second pillar, tool adaptation.
Exactly. When the tool learns, who's in charge of that learning? The first form they identify is agent-agnostic adaptation.
Agent agnostic, so the agent has nothing to do with it.
Nothing directly. Think of the tool just improving itself in the background, through system logging or A/B testing. It's optimizing over time, completely separate from any one agent that's using it.
So the tool is basically updating its own software. Makes sense. What's the other form?
That would be agent-supervised adaptation. And here, the agent, usually the LLM is the one that spots a problem with the tool and then actively works to fix it. It might generate new instructions or even code to improve the tool for the next time.
Wow, okay. So the agent is acting like a manager. It's submitting bug reports or even writing the patch itself.
That's a great way to put it.
So that distinction is it's incredibly useful. We've gone from this huge, confusing landscape of different methods to a clear four-part system. It's all about who adapts agent or tool and what signal makes it happen.
And that framework provides really practical guidance. It's a conceptual foundation. It gives you a roadmap for choosing your strategy based on the problem you're trying to solve. Are you worried about latency, reliability, generalization? This helps you decide.
That structure is exactly what was needed. It helps us all move past that feeling of information overload.
And if you connect this to the bigger picture, it really sets the stage for what's next. So here's a thought for you to take away. How might a future system, intelligently combine these signals? Imagine using that fast, low latency tool feedback for minor corrections, but also having the agent supervise and rewrite its own tools when it hits a major wall. That's how you get to systems that can handle truly complex tasks and, really learn continuously. That's the next frontier.